So today, let's talk about something that sounds a little bit like science fiction. What if you could build your software with actual mathematical certainty? I'm not just talking about well-tested code, I mean provably correct right from the ground up.
Okay, so right off the bat, let's get one thing straight. This isn't some theoretical paper from a university lab. Nope. We are talking about a complete, production-ready system that's built for the real world. It's a framework you can use today to build deterministic, distributed systems.
And when I say production-ready, I really mean it. Look at this. For starters, it's got a modular architecture, which just makes everything way easier to manage. It uses formal verification. That means you can actually prove that its properties are correct, which just wipes out entire categories of bugs by design. You get deterministic execution, so the same inputs always give you the same outputs. No randomness, no surprises. And of course, it's all built with modern practices in mind. Comprehensive testing, easy Docker deployment, and full observability.
So that's the big question, right? How on earth does a system pull this off? How can it promise something as bold as mathematical proof and achieve consensus without things like voting or having a central boss? Well, the secret sauce is really in its unique architecture.
To really get where all this power is coming from, we've got to peel back the layers. The whole system is designed with this really clean, hierarchical structure, where each layer stands on the shoulders of the one below it, inheriting its guarantees.
It's got 4 distinct layers. It all starts at the very bottom, at the foundation, formal mathematical proofs. On top of that, you have the core deterministic algorithms. Layer 3 is where you get your APIs. These are your contracts for talking to the outside world, which is obviously crucial for integration. And then, finally, at the top, layer 4 is where all the services get coordinated. Everything, everything, flows up from that solid mathematical base.
But running through all these layers, there's this one single, really powerful idea that ties it all together. It's the philosophical core that makes all of this possible in the first place.
And that core idea? It's called BICF. Yeah, it's an acronym, and it might sound a bit technical at first, but trust me, the concept behind it is actually pretty elegant once it clicks.
So BICF stands for Boundary Interior Combinatorial Framework. The big thing to remember here is that it's a formal mathematical foundation. It's basically a rule book for how to design systems so that they are verifiable just by their very nature.
The whole thing really makes sense when you get this split between boundary and interior. The boundary, that's the set of ironclad, unchangeable rules. Think of it like the laws of physics for your system. The interior is the actual data that lives and changes inside that system. Let's take a bank ledger, for example. The boundary would define an absolute rule like an account balance can never be negative. The interior would be all the transactions happening. Any transaction that would break that rule isn't just flagged as an error, it's mathematically impossible within the system's design. The data can evolve, but it can never, ever violate the boundary.
This quote from the creators just nails it. It's all about using those immutable boundaries to allow for safe variation in the data. This is what lets the system achieve consensus based on math, on combinatorial guarantees, instead of relying on messy, unpredictable things like probability or just trusting one central server. Correctness comes from the design, not by chance. Okay, so here's the bottom line. By separating the rules from the data so strictly, you can actually prove things about your system. And that simple idea unlocks some absolutely game-changing ways to handle data. Let's look at a perfect example of this in action.
Let's get practical. Let's talk about something called the Native Repository Runtime, or NRR for short. This is a fantastic example of those BICF principles creating a real-world tool that solves some huge problems.
So what is it? Well, think of the NRR as this super minimal, super clean repository abstraction. The 2 key phrases here are get independent and deterministic replay. It's designed to give you all the core goodness of a content address system, but without locking you into a specific tool like Git. And this really flips the script on how we usually think about Git. In this system, the NRR is the core engine. It handles the critical stuff, content address storage, and an append-only log. Git? It's not a dependency at all. It becomes this optional layer on top that you can use for things like transport or just as a familiar UI for developers. The system itself could not care less if Git is there or not.
And this is a huge deal, and here's why. Because the NRR is so incredibly minimal, it doesn't even need to allocate memory on the heap. It is perfect for microcontrollers. You can deploy systems built on this on tiny little embedded devices like an ESP32 or run them in a browser with WebAssembly. It's completely binary safe, and it gives you that rock-solid guarantee of perfect, deterministic replay from its logs. This is what makes real, verifiable integration possible across totally different platforms.
So, when you put it all together, the formal proofs, that boundary interior idea, and innovations like the NRR, you start to see that this isn't just a new tool or another library, it's a whole new discipline for building software.
The creators call it a discipline of construction, and it really boils down to this three-step process. 1. You define immutable boundaries. Make every single constraint explicit and verifiable. 2. Every operation executes deterministically. No hidden state, no side effects. And 3. You verify the whole thing formally, with machine-checkable proofs that guarantee it's correct by design.
We're talking about a fundamental shift in how we think. We're moving away from this world where we write a bunch of code and then run test after test, just hoping we catch all the bugs. Instead, we're moving to a world where we can actually prove that entire classes of bugs are mathematically impossible from the start.
So that leaves us with a pretty powerful question to think about. From critical financial systems to the Internet of Things, running on millions of tiny devices, what new kinds of applications become possible? What could you build if you knew with mathematical certainty that your system was correct?